Hello and welcome. In today's presentation, I would like to talk about two very common but very interesting subatomic particles. The word subatomic means they are even smaller than atoms. Just try to imagine shrinking yourself down to the size of an atom, then seeing even tinier things whizzing around you. These things are electrons. Every atom has a dense nucleus at its center, and at least one electron in the surrounding space. The nucleus is positively charged, and each electron carries a negative charge. On familiar human scales, positive and negative charges usually attract each other and snap together. On subatomic scales, there are strange quantum effects that stop the electrons from snapping into the nucleus. They still feel an attraction, but they are forced to stay a certain distance apart. Instead of being arranged in a random cloud, the electrons orbit at fixed distances from the nucleus. This is what physicist Niels Bohr stated over 100 years ago, when he drew a quantum model of the hydrogen atom. Bohr stated that electrons exist in energy shells. The further a shell is from the nucleus, the more energy is contained by electrons orbiting there. He also calculated exactly how much energy is associated with each shell in a hydrogen atom. You can do this with any atom, although it gets complicated when the atom contains more than one electron. It's possible to give an electron some extra energy and make it jump into a higher shell. That energy can be delivered by the second subatomic particle I mentioned. It's called a photon, and it is not bound to any atom. In fact, it's the fastest thing in the entire universe. Streams of photons are known to us humans as light. Every time you turn on a lamp, photons fly out of it at 300,000 kilometers per second. Some go straight into your eyes, providing you with the image of the glowing lamp. Other photons go in other directions, bounce off the objects in your room, and then bring information about those objects to your eyes. As you'd expect for something so fast, a photon is quite energetic. The exact amount of energy it carries is linked to a property called wavelength, which also determines its color. Light with a red color is composed of photons with a long wavelength, and inversely, a small amount of energy. Blue or violet light, at the other end of the spectrum, has a shorter wavelength but carries more energy per photon. Let's see what this means on the subatomic scale. When a photon travels into the space around an atom, it may collide with an electron. When this happens, the electron absorbs the photon and takes in the energy it was carrying. If the right amount of energy is absorbed, the electron can jump to a higher energy shell. We say the electron is excited. Just as with humans, excitement wears off after some time. This electron cannot stay in the higher shell for long. It must return to its original position. As it returns, it produces a new photon that carries the same energy as the difference in these two energy shells. This new photon may strike another electron and repeat the process, or it may simply leave the atom. What I've been hinting at, and what Bohr insisted on, is that these energy shells are fixed at very specific distances from the nucleus. In other words, the amount of energy associated with each shell is very specific. This is actually what quantum means, that on this scale, everything depends on specific quantities of energy. When a photon strikes an electron, it must transfer exactly the right amount of energy for the electron to jump to the next shell. If there is too little energy or too much, even by a slight amount, there will be no jump. It's like paying for lunch, except if you pay too much you get no change and no lunch. When an electron returns to its original shell, the photon it emits carries the exact amount of energy associated with that jump, so it only has one possible wavelength. Photons of a certain wavelength are needed for excitation, and photons of a certain measurable wavelength are given off after excitation. Can you guess where this is going? I've also said that the gaps between energy shells differ depending on the type of atom containing them. Atoms of helium have a different configuration of shells than atoms of hydrogen, for example. Therefore, the photons given off by electrons in each element have different wavelengths, or different colors. This means that if you shine enough light on something, it will emit light with a specific color or range of colors. You can see the colors, or use a device to measure their wavelengths, and work out which elements are inside the thing. This is the core principle of spectroscopy, using light to work out what objects are made of. Spectroscopy will be explored properly in future videos. For now, here is what you need to know. Bohr's model of the atom describes a positively charged nucleus surrounded by negatively charged electrons. The electrons are arranged in circular energy shells. Each shell is associated with a specific amount of energy and located at a specific distance from the nucleus. An electron can jump to a higher shell if it is given the right amount of energy by an incoming photon. However, it can't stay there for long and will jump back down, releasing another photon in the process. Because the specific energy levels are different in different elements, if we capture this new photon, we can work out which element the atom belongs to. That's all for this video. I hope you found it a helpful introduction to quantum physics. If you want to know more about this topic, please let me know in the comments below. I would also appreciate it if you could like the video and subscribe to my channel to show your support. Thank you very much for watching. Good luck with your studies.